we have learned a lot of stuff. Previous lesson, we were dealing with summation notation, which is basically adding an infinite number of rectangles together. And then, although we didn't really go through that process, we talked about how to set the problems up to where it could be done. We also dealt with trapezoidal sums, left Riemann sums, right Riemann sums, midpoint sums, fundamental theorem of calculus in two different presentations, two different ways of thinking about it. A lot of stuff, but it's really time we get to the big idea in all of this, kind of sums it all up. Bad pun, but antiderivatives. Not like we're against derivatives. I'm in favor of derivatives because they're so incredibly practical. And here it goes. What we're going to do for this first little part of the lesson is we're going to talk about, oh my goodness, I gave you f prime, find f. So we're just going to take this and work backwards. We did this a little bit with the fundamental theorem of calculus, the second presentation of it, two different lessons that dealt with that. So the fundamental theorem of calculus involves an antiderivative, but now we're just going to get some practice with an antiderivative and figure out some strategies for consistently finding an antiderivative. So here we go. The directions are going to be to find f, so whatever the function is. And our first problem is I give you f prime, and it is 2x, and then I say, okay, what function would have a derivative of 2x? Now, when I take a derivative, I would multiply coefficient times exponent, and that becomes my new coefficient. I would take my exponent and I would subtract 1 away from it. So what I really need is some function that if I took its derivative, I'd get that. So I need an exponent to be higher than what it is right now. I need it to be 1 higher, so we'll go for the obvious. And then we also need this times 2 to give me 2. So the derivative of this had better be this, and it is. So like 1 times 2 gives me 2. Mission accomplished. We now have one of the ways, one of the possible functions that could give us this as a derivative. Now, like, what do you mean? One of them. That's it. I agree. That is it. The derivative of this is that. But the derivative of this is also that. And the derivative of this is also that. And the derivative of this is also that. We could have a constant. It could be negative. We don't know what it is. We could have a constant there at the end, and then when you take the derivative of that constant, it goes away and you're left with this. So as we continue this conversation, and as we do this, we have to consider that there was something that we don't know, and given this context, we don't have enough information to know. And so there will be, in every one of these problems, a constant at the end. We're going to put plus c. Now, the obvious question is, what if c is negative? Why do you put a plus? Well, then c is negative and you're adding a negative, and that's totally okay. Okay, let's move on to the next problem. Do not forget the c. I used to have a little rule. If you ever forget a c, you have to tell an embarrassing story on yourself. That rule still applies. So if I forget it in this lesson, I'm going to have to tell an embarrassing story on myself, right? If I forget it in the video, so I better not forget it. So we need the derivative of something to give me 4, and I would like to think it's obvious, and if it's not, that's fine. But the derivative of something gives me 4. Well, first of all, it's giving me a constant, and because it's giving me a constant, the derivative of a linear is a constant. We did this lesson where we talked about, well, the derivative of a cubic is quadratic, the derivative of quadratic is linear, the derivative of linear is a constant, right? So you could say it's this. Just saying. So all that, keeping that in mind, basically we're adding 1 to the exponent. So we're going to do that. And then something times 1 would give me 4. And the rule is, if I move on to the next problem and have forgotten a c, then I have to tell an embarrassing story. And that rule applies to you as well, for those that are in my classroom. So stop and make eye contact with the camera. And then plus c right there. So now I'm ready to move on to the next problem. And the next problem is a full-on polynomial. F prime of x equals 12x squared plus 6x plus 7. The others were polynomials, but they just didn't look like polynomials. And is that whole thing showing up? It is, it is. I get right up in the camera. So we are going to figure out the antiderivative. Like if we took the derivative of our answer, we would get the original function. So plus c at the end. We'll get there in a minute. Every exponent is going to go up by 1. So it was squared, now it's cubed. It was to the first, now it's squared. It wasn't there, and now it's there. Plus c, taunting taunting myself, like playing with it, just thinking, okay, I'm gonna forget the C here. I'm not gonna forget the C. I better not, right? So something times 3 gives me 12, must be 4. Something times 2 gives me 6. Something times 1 gives me 7. Well, I guess I'm done. No, I'm not. Ha ha. Gotcha. Everything's positive, by the way. And then plus C. And I'm not sure if it's showing up on yours. It doesn't look like it's showing up on my screen, but I did write plus C, I promise. So let's move on. By the way, good way to check your answer, take the derivative. So we're going to go on to the next one, and things get a little bit less polynomial-ish as we move on to the next one. I'm going to erase what we have, and we'll just keep our 3 problems. Throw the eraser on the floor. How about that? Get eraser dust everywhere. My next 3 problems are cosine of x, x squared, and negative x minus 5. And we are going to figure out the antiderivative of each of these. I hope you remember, I truly hope you remember, this fun little rectangle of trig derivatives. If I wanted the derivative of sine x, it would give me cosine x. The derivative of cosine would give me negative sine x. The derivative of negative sine gives me negative cosine. The derivative of negative cosine gives me positive sine. Knowing all that, I can move backwards. So clearly not a polynomial, but the antiderivative of cosine would be sine plus c. So sine x plus c. We're just moving backwards here. So final answer. That's a funny looking parenthesis. It looks like an onion with an x in it. Sine x and then plus c. Okay? Now things get a little bit tricky, even though you're like, oh, it's a polynomial, we can do this. I agree. You're right. So f of x equals, okay, I'm going to add 1 to my exponent, and that gives me x cubed. And then I start thinking, okay, something, if I took the derivative of this, something would give me a 1 in the front. So there's a 1 right here. And I have to kind of think my way through it. Something times 3 gives me 1, and it's not an integer at this point. So most of everything we've done so far has just been integer, happy little integer. Well, now it's not. So something times 3 gives me 1. I'll go ahead and tell you what it is. If I took a third of 3, I'd get 1, which I know that and you know that. We both know that. So it'd be 1/3. However, no, I haven't forgotten my C. However, you will often see this written a different way. So I just want you to be aware of the multiple ways this could be written. This could be x cubed over 3, which is something we know. It's like multiplying fractions, right? So it's x cubed is technically a numerator, gets multiplied by that 1. Either one of these is valid. Let's see, for both of them. I'll accept either one. I think at this point, though, it's a good idea to kind of stop and think about a good way to figure out what the coefficient is when it's not as obvious. So, I wonder how we can get this 1/3 based on the numbers that we see here. Just be thinking about it. We'll move on to that in a second. All right, the next one. Let's see, it was linear. I am going to undo. My derivative is linear, so my original function is going to be a quadratic. So I know it's squared. So x squared on that term, x on that term, c at the end. So I want to know, again, trying to think of my coefficients and a good way to figure them out. I want to know what my coefficient would be on that x squared in order to get a negative 1 right here. So something times 2 gives me negative 1. Some number times 2 gives me negative 1. Well, then in that case, it would be negative 1/2. So negative 1/2. Let's just kind of stop and think about it. Let me reword things. This was my old coefficient. Negative 1 right here was my old coefficient. 2 was my new exponent. So the best way I know to explain it is this. Old coefficient divided by new exponent gives me my new coefficient. I'm going to say that a lot. Old coefficient divided by new exponent gives me my new coefficient. We're going to write that down on the paper in a minute. Let's move on. Old coefficient, negative 5, divided by 1 gives me my new coefficient. Are you ready to move on? I'm not. Let's see. There we go. Making sure I haven't forgotten any C's. Forgot them on an answer key one time. I go back and put it in and scan the whole thing again. Mr. Reader, you owe us an embarrassing story. Do not. Okay, I hope you remember a lot of the very obscure derivative rules, and if you don't, please, please, please review them. They're good to know. We're going to need them as we move on to, well, some of the more obscure things. And this next one is one of them. So if we had secant squared x, there's one thing, and then we'll do square root of x, and then this one is going to be 4 over x squared. All right, here we go. The derivative of something gives me secant squared. Now we can get all crazy with the trig and the little circle, or well, the thing we had down here. Nah, let's not. It's a square, not a circle. But that's not related to that really at all in a sense. The derivative of something is secant squared, you just know it. The derivative of tangent is secant squared. And then there could have been a constant at the end. We could have added whatever. And the derivative of c gave me 0. So plus 0 here. All right, the next one is going to involve a rewrite. The next two are going to involve some rewriting. I remember when we were doing, I hope you remember too, when we were finding derivatives and we would have to do a rewrite in order to figure out a derivative. Now we're going to do a rewrite to figure out an antiderivative, and it looks like this. This is x to the 1/2, and this is 4x to the negative 2. Just good to know, okay? And again, no c's yet. I've seen students like, oh, I can't forget my c. Yeah, well, you haven't. You haven't taken the antiderivative yet. So random story in the middle of a video. At MIT, they do a what's called an integration bee, and they will put these students, like these crazy math students, crazy in a ridiculously smart way, against each other, like spelling bee, but it's like, hey, integrate this, and whoever can do it right in a certain amount of time gets credit, and they don't make them put plus c at the end, and that just drives me nuts. Anyway, so we are going to find the antiderivative, and don't make it harder than it is. The same rules apply. Everything you've done up to this point, not the trig stuff, but everything you've done up to this point applies. Add 1 to the exponent. Okay, sounds good. What is 1/2 plus 1? That would be 1 1/2. 3/2, okay? And then, well, how are we going to figure out our coefficient? You have a couple ways of thinking about it. Something times 3/2 gives me 1. I wonder what it could be. Don't know. You can figure it out. Or you could say old coefficient divided by new exponent, which gives me 1 times 2/3, which is 2/3. So 2/3, and then plus c. And if you want to rewrite what you have, that's fine. I don't have to, but I could. I'm going to, because I feel like it. This is the same thing as 2/3 times the square root of x, and it is cubed, and then plus c. And there's a little more we could do there. Factor out an x, and we'd have 2/3 x, square root of x, plus c. We're not going to go there. Don't worry about that. Okay, last one. And we are going to find the original function. Panicking, making sure I didn't forget a c. I didn't. Off to the side, I have somebody like holding a poster like, don't forget your c. And then they leave to go to the bathroom, and I forget a c. All right, I'm going to add 1 to my exponent. I get a -1. 4 divided by -1 is going to give me -4. By the way, what just happened was old coefficient divided by new exponent. Or you could say something times -1 is going to give me 4. So it's going to be -4 and then plus c. This is valid. This is also valid. Either one of those is going to work perfectly well. So right below that, it says when finding the antiderivative of a polynomial, and it applies in non-polynomial contexts as well. These aren't polynomials, but it applies. So whenever I have, let me erase some stuff here. Whenever I have some polynomial as a derivative, like f prime is equal to ax to the n, and n is some integer, if it's truly a polynomial, or just whatever number it may happen to be, or a is just some constant. Basically, a and n are constants. Then, here we go. Add 1 to your exponent. And then, old coefficient divided by new exponent. And it seems like, oh, I have to memorize all that stuff. You just memorized it by doing all those problems. You know this. Plus c, right? Okay. And just in case you need it written down, old coefficient, if I could spell, that would just be fantastic. Old coefficient divided by new exponent equals new coefficient. That's just the little thing that plays over in my head as I do that. There we go.